conditional probability. So conditional probability, essentially all this does is it's saying that we're finding the probability of an event happening given that we know something else has happened. Okay? So it could be, so how many of you do psychology? 1, 2, 3, 4. Okay, so it might be, we would say, often, we'd say, what's the probability that someone does psychology in ID1? So we would say, how many students do psychology, how many in a class?
In my class?
10. In total. Let's say 20, okay?
In your class? There's like 6 and more. 16
then. Okay, we'll go 16. And then, how many people in ID1?
32.
33.
Let's say 30. Say 30.
Right. It doesn't matter.
Why don't we just do 15 and 30?
Okay, we'll do 15 instead. All right. So there's 15 people that do psychology. There's 30 people in the year group. So we would say the probability of psychology is 15 over 30. Okay. But what we're going to now say is, okay, what's the probability that someone takes psychology given that they're actually in my maths class? So automatically what we've done is reduced our pool of people from 30, whatever it is, to just 9. Does that make sense? Mm-hmm. So then that means our probability is now 3 or 4 out of 9. Yes? Because there's 9 people in this class. Yeah. So conditional probability is all about that. So how it's formed is that we say, well, what's the probability that someone does both of those things? So you would first of all establish what's the probability that someone is in, does psychology and also is in my maths class. So we would find out those number of people. So that's that probability over the probability that someone's in my maths class. So we would say 9 out of whatever. Okay? So that's how that's formed. Do you understand the concept of conditional?
Can you say that like B is like a definite event and it's like A is the more uncertain event?
Yeah, I guess so. Yeah. So yeah, for sure. Because this has to happen. You're only talking about people that are in that group. Okay. And sometimes you can get away with finding probabilities by just thinking about numbers of things. So like we did, we said that there are 9 people in here and 3 of you do psychology, so it's 3 over 9. Sometimes it's a bit more complicated and they give you the probabilities of these things happening. And it's not always out of the same numbers. So here we go, 2-fair die are thrown, find the probability that 1 dice shows a 4, given that the total of the 2 dice is 10. Well, when it comes to dice being thrown, we've got 2 dice being thrown, you have to establish yourself, you have to establish what options you have to start with. Now, sometimes that can be tedious. And did we have this situation the other day where there was 3 things happening? We were like, how do we draw this? So you have to try and think of some systematic way of making sure you've got all the different options. So here we've got, start with a 1, 2, 3, 4, 5, 6. So we can see there's 36 options there. Yeah. If we want to know the probability that a dice shows a 4, given that the total of the 2 dice is 10, we need to find those situations. So so that a 4 and a 10 would be just these 2 situations, and a 10, totals up to 10, would be these 3. Yes? So from this, realistically, we could just say that it's 2 out of 3. We know that's what our answer is going to be, because 2 of those situations are what we want out of a possible 3. However, if we were talking about the probabilities, we could just write them like this. 2 out of 36, or 3 out of 36. And we know that when we're dividing fractions, how do we divide fractions?
You change the
So if we change to a
line.
They cancel each other out, which is 2 over 3. Okay? But as I said, in that situation, we could have just gone straight to the 2 over 3 because we knew the numbers of the events happening. And sometimes it's not quite so. Okay? This one's a bit more complicated. So we've got, given that we know the probability of A, we know the conditional probability of A happening given that B has, and we know the union. We need to find the probability of B. Okay? The fact that they've got the union happening there and the probability of A, they've asked us for the probability of B, would lead me to thinking that we're going to be using this formula at some point. Do you remember we learned this the other day? Yeah? So you get given it. So the fact that they've told us the union and A and they've asked us about B probably means we're going to be using this. Now, the issue is that we don't know anything about the intersection, but they did tell us about the conditional probability. So we know that conditional probability would be this. Yes, so I've changed my letters to the A and the B. So I know that this is 1/4. I know it's this over this. So I could actually rearrange this to be that the intersection is 1/4 of PB. Yeah? So I still don't know what PB is, but I know that the intersection is 1/4 of it. Okay? So that means that now I can stick that information into this formula. So I knew that the union was 2/3. I knew that A was 1/2. I don't know PB. And I know that this is 1/4 of PB. Yeah? Coming together nicely. Rearranging, so I'm going to subtract half from both sides. And I've got 1 PB, subtract 1/4 PB, gives me 3/4 PB. You agree with that? Because 1/1 would be 4/4. Yes. So 4/4 take away 1/4 is 3/4. Adding, subtracting fractions, it could be on the non-calc paper, so you do need to remember how to do it. How do you add or subtract fractions? What has to be the same?
Denominator.
And what denominator will we have?
6.
So we need to change these to both be 6s. So what do I have to do to this one? So that means the top has to be multiplied by the same. Yeah. So that would become 4/6. And what do I have to do to this one?
3.
And that would become 3/6. So 4/6 take away 3/6 gives us 1/6. Yeah. And that's still equal to 3/4 PB. And then we just rearrange this to find PB. So I know that PB is going to be, are you happy that I multiply and cross multiply? So that's 1 multiplied by 4 over 6 multiplied by 3, which gives us 4 over 18, which we can simplify to 2 notes. So it's all written on there. Like sometimes I know it's good for you to fill stuff in. And I apologise if you don't actually take anything in. Today's probably the worst day if you don't actually write anything because you're going to keep fall asleep. But you may want to add a few notes or notes to yourself, remind yourself that's how you subtract fractions and say it tends to be the situation that people get to IB and forget their early learning stuff. And if it's on a non-calc paper, then you're in do. Okay? So from that one, as I say, it tends to be a situation where you look at the information they've given you, look at the formulae that you've got, and that one of your formulae may help you with another. So it's not always just a straightforward question, and it could be a little bit more involved. Independent events. So if things are independent, it means that one event does not affect the other. And that means that if we're talking about the probability of A given that B has happened, well, that means that it would just be the same as probability of A happening anyway, because that indicates that the event B has had no impact on what we're talking about. Does that make sense?
Yeah.
So the probability of A, given that B has happened, if that's exactly the same as just the probability of A, it means that this has had no impact on it. Yes. So if none of you did psychology, no, that's bad example. If none of you were in my class, then it would be the same probability as if it was just what the probability of doing psychology. But some of you are, therefore that's why it's changed. Yeah? Oh no, I lost. I went back to the thing the conditional thing we were talking about earlier.
No, I got the link.
Oh. Yeah, I know, but it just didn't work because I had to shut up. The given that was that you were in my class. It's not doing well. So I can't. Anyway, now we've just recorded all that. The probability of A given that B is this formula. Yes? So that means that this is equal to this, which means that the intersection will we just multiply our two probabilities together. Which we probably knew anyway. It tends to have been something you would have learned a while ago, that the probability of A and B happening at the same time, you would multiply your two probabilities together. Yes? Like tree diagrams? Oh, we can understand. So a card is picked, a random pack of cards, a die is thrown, so does pulling a card out of the pack and rolling a dice have any impact on each other? No, none whatsoever. So they're independent events, which means if I want to know the probability that it is an ace of spades and we get a 3 on the dice, we would just multiply those together. So it would be 1 over 52 multiplied by 1 over 6. Any still. Okay? But we can do that multiplying because they are independent. Not. So mutually exclusive means that there's no intersection. So independent means, what's the difference between exclusive and independent? Let me come back to that. Let me think of a good way of saying it. Yo.
That's in the bracelet?
No.
Really? Like your earrings. Your friend's house. I said to her outfit today looks nice. It looks very on point. Like, to be that.
It's perfect. Oh, your next friend is like that too?
It's not something I believe. No, it's not. I thought she liked it. She would have.
Alright, it's Betsy Boo Form today. Thanks. Everyone now knows I'm not Betsy Boo Form here.
I'm scared.
Yeah.
Bye-bye.
Should we just finish this and then we can chit chat whilst we're not being recorded on YouTube for anyone in the world to see? Or hear.
I hope they hear this.
So, tree diagrams. Do we remember tree diagrams? Did we like them or did we not like them? Oh, shut up! We I love a bit of tree diagrams.
Easter. Like 3 times.
It was in teacher.
We spent like only 3 lessons before probability, and it was like right before our exam.
Okay.
It was long.
Oh, but then this probably is not a good example then, because I've gone straight for hard stuff. Whoa. Well, because I was kind of hoping that you would have liked it. Alright, there's lots of words here, and all of these words are very important, because I wrote them. I can't bother to read them just now, so I'm just going to explain probably what that means. Okay?
Probably.
Oh, I didn't like So, okay, these are the key points. So let's ignore the probabilities just for now. So the key points about tree diagrams is that each portion of the tree talks about an event that's happening. So this here would indicate that in a bag I've got red and blue discs, and that I can take out a red disc or a blue disc. So that's where I got that branch from. Now the fact that I've got a second set indicates that I'm doing that for a second time. Yes? And then the fact that I've got a third set means I've done it for a third time. Okay? So each of these things progress depending on how many things you're talking about. Now, these red and blue aren't necessarily going to be the same for every question. So it could be that we've got this set talking about traffic lights and this set talking about something else. Okay? So these options don't always have to be the same as each other. A lot of the time they are, but they're not always. So just hang fire if they're not. Well, I feel, do I need to go more basic? Do I need to go? All right, okay. Now, do be careful though. So, if you're ever asked to draw a tree diagram, which I can't imagine, normally it's a complete tree diagram. But if you are, you need to make sure you go wide enough that you've got space to draw some more branches if you need to. So note, I've got 2 branches here, I've got 2 off each of them, and then I've got 2 off each of those. So it gets quite busy quite quickly. Now, then we talk about probabilities. For this section here, my two probabilities here have to add to give 1. Because I've got two options, those probabilities must add up to give 1 whole one. Okay? This shows me that I had 4 discs that were red, 5 that were blue, so I had 9 in total. So I can see that information from my tree diagram. Now what's happening in these instances is that we're taking the disc out, but we are not putting it back in the bag. So the fact that we are not putting it back in the bag means that my probabilities are now going to all change. So my probabilities for my second set are different. Now notice these are not the same as these. Because these ones up here are following the route that we took a red disc out first. And so my suggestion for you when you're doing a non-replacement is that the first thing you do is say, right, we had 9 to start with. I've got 8 now. So first thing is write your denominator. Okay, so you've got only 8 in your bag. Then you say, right, if I follow this branch, it tells me that I would take the red disc out. So where I had 4 before, I've now only got 3. And then you say to yourself, well, I know this has to add up to 1 whole one. So it means I must have 5. Does that make sense? Yeah? So do your denominator first, then your top number, the numerator of your top one, and then just fill in this afterwards to make 1 whole one. It also makes sense because this shows you that you didn't take any blues out, so you still have the 5 at the start. To do this bottom one, follow the blue, which means when there was 5, there's now only 4. Which means that this has to be 4 as well, because that's out of 1. Yep. Same thing, or a similar thing for the third set. Now we've only got 7, so all of them have 7. Follow the red, and then we've got 2, and 5, so on and so forth. Yeah? And this bit here at the end just summarizes what we're looking at. So this follows a red, a red, and a red. So it means that we're showing we had 3 reds. Red, red, blue. Red, blue, red. And notice I write them at the ends of my branches. I don't just randomly write them. They're actually at the end of the branch. Yeah?
What if you find 4? That's what you multiply.
Yeah, you multiply.
5 over 4.
The 504.
Oh, I'm going to show that now. Right, I haven't got that yet. So these are our options. Then we say, okay, well, what's the probability of getting a red, red, and a red? Now, we're using the word red and red and red. When we are multiplying, when we are doing things and something else, we multiply our probability. Just shush. So red, red, red would be 4 9s multiplied by 3 8s multiplied by 2 7s. 9 multiplied by 8 multiplied by 7 gives 5 over 4. So you'll notice because we know that's our denominators for every single one of them, then we keep that as our denominator. So then our numerator would be 4 multiplied by 3 multiplied by 2. Okay, then you would do that. These probabilities in this row, this column here, have to add to give 1. Okay? So if they don't, if they add more than 1, you've made a mistake.
They all have to equal the denominators? Like
Yes.
504.
So essentially, these numerators have to add up to 504.
But they don't.
Yeah, they're supposed to.
They just numerically possible.
Yeah.
There's a 4 there somewhere? Oh, the 24. That.
I mean, you got it pretty good, though. Okay? So we multiply across branches. Now, should we want to say, okay, well, I want to know 3 of the same colour. So I want to know this situation or 3 reds. Then what do we do with those probabilities? We add them. Yes? So something and something else means we're multiplying. And something or something else, we would add those probabilities. So we would find the situation and add them. So here they've said find the probability it's 2 red and 1 blue. So we're looking at this, this, or this. So we would add those probabilities and we get 5 over 14. Now, the fact that I keep it with my original denominator and I don't simplify it means that this part is a lot easier because I've already got my denominators being the same. So whilst they often do simplify, it's often easier to leave them not simplified. Okay? So this would obviously be 180 over 504, and we can even leave it like that because we know probability, we don't have to simplify it much. Okay? Right, so that's not natural. Stop. Stop saying 9. Oh, still above. I'm still recording. I can't stop it.
Harrison, what brand?